So today is actually kind of a bridging session between what we now learned about the GLM and how we can estimate parameters, and what you are also very familiar with respect to the GLM, namely computing t values and f values. And today provides the link between these concepts. And I think it's a very important session because it's something that is not that much discussed, and somehow in undergrad statistics you are told that the t values have a distribution, but it's not quite clear where it's coming from, or where these distributions come from. And I think actually the distributions of the estimates, they really provide this crucial link. So the first thing I want to talk about is the intuition about these estimate distributions. So roughly where they're coming from, essentially. Why are they doing this? Then the beta parameter distribution. And then, of course, the variance parameter distribution. And I think actually the importance really of this session is in, like most of the time, but today especially, in the intuition, so that you get into the right way. Maybe you are already, but maybe you can get a little bit further into the right way in thinking about the frequentist story about the GLM. And let's start with the intuitive bit. So, we are currently at the following stage in our understanding of the GLM. We started out with this equation, and where, like always, our y is an n-dimensional vector, the x is an n times p-dimensional matrix that we know. Beta is an p-dimensional vector. Our epsilon is also n-dimensional. Our 0 as well. The identity matrix is clear, and sigma square is larger than 0. This we've seen many times, and from this we discussed that this makes the data distributed according to the random variable modeling the data, distributed according to a multivariate Gaussian distribution with an expectation parameter given by the product of the design matrix and the beta parameters, and a spherical covariance matrix, which also models the independent error terms for each individual data point. Based on that, and that essentially specifying a likelihood function, we last time figured out that maximum likelihood, or ordinary least squares estimates for beta are given by the multiplication of a data realization by the inverse of the cross product, if you want, of the design matrix times the transposed design matrix, and an unbiased estimate of the variance parameter is given by what is also called the residual sum of squares here in the numerator, divided by n minus p. This is a p-dimensional thing, and this needs to be larger than 0. Just because you have a square larger or equal to 0, it can actually be 0. Just because it's a square in the numerator. Okay, so this is where we went up to, and now you need to think again about what this means from a frequentist sampling perspective. So the idea is that the data is distributed according to this multivariate normal, which, if you think now about your basic MATLAB skills, if you know that there's a random number generator that generates normally distributed numbers, this can of course be generalized to a multivariate Gaussian random number generator, and once you specified these parameters, so you specified your design matrix, a beta parameter, a sigma square parameter, then you can happily sample values from this distribution. Yeah? So this should not be that surprising. You can only do that, however, if you specify beta and sigma square. In the script, I here also give them a bar to basically signify that I mean specific and fixed, true but unknown values. No? So these are parameter values. For example, if you are in the simple linear regression case, you know that the beta is two-dimensional. So this, for example, would be true but unknown values for the beta parameter, yeah? 1 and 2. And this would be a true but unknown value for the variance parameter. So usually I don't use this extra notation here. So oops, this was supposed to be a bar, not a estimate, not a head. So I'm just telling you now that when here I mean a true but unknown beta parameter value, and here I mean a true but unknown sigma square value. Yeah, so you put them into your random number generator, and then you create a sample. And this sample I now call y1, just because. Keep in mind that this is of course a vector, right? So this 1 here now doesn't mean the first entry or something. It means that you have realizations y1 from 1 to n. Yeah? So it's the vector. Now, once you have this realization, you can, of course, apply the formulas for the beta and sigma square estimates, and you obtain essentially the transformation of the data given by these formulas by just plugging your y1 into this, and then using the formula for the variance estimate and the estimate of beta, t y1 minus x beta 1, to compute values here for your beta parameter estimates and your variance estimates. So assume that these are actually the true but unknown values, so that we now have the true but unknown values are 1 and 2 and 0.5. Then, depending on how much, if you want noise or bias or whatever there is in the first sample, you know how the error is parameterized, but of course from sample to sample there will be a little bit more, a little bit less of this. A possible estimate then here, for example, would be something like 1.1 and 1.9. So roughly that, but not quite, because there's a little bit of randomness. And here, for example, would be 0.52 or something. Yeah. So you sampled once and you obtained estimates for this sample. Now, of course, you can think that you sample again, here y2, and again compute your estimates. And in this case, let's say they are like 0.9 and 2.05 and maybe 0.53. Well, now you can do that again and compute for the next sample the estimates. There's a thing missing. And get, for example, 0.95, 2.10, and 0.48. Yeah, and of course, this could continue, so you can compute, so you can realize a lot of samples, and then get also a lot of, if you want, samples for your better estimates and for your variance estimates. And what we are now interested in is actually to give analytical or closed form descriptions of the distributions of these estimates. Yeah? So you can think, of course, if you have these many samples, that you do a histogram and look at how the values look. Here you would have to do a 2D histogram, and we will see that later on. And for the variance, you have just a 1D histogram, which we will also later look at. But we are looking now for closed form analytical expressions for the distributions of this. Yeah? So this is what we are interested in. These the distributions of these virtual, or now just this virtual realizations of the estimates beta and sigma square. Now, how does this relate to actual data analysis? And this is very, very important, and this you should now, from now on, always remember. But I guess I will come back to it. So this so far has just happened in my head, maybe your head, maybe if you implement it on a computer. But it has nothing to do with real data. Now, the thing is, if you have data, so you have, for example, you observed some data y, which is a 10-dimensional vector. For example, if you have 10 values, so you do a simple linear regression with 10 values or something, then, and this is the crucial thing, then you assume that this, what you have observed, your data, that's the data, is one of these realizations that you could potentially take from this model. Yeah. So although you only ever have one realization of data, you pretend that there is a multivariate Gaussian distribution behind it, which you assume is maybe somewhere out there in the world, with true but unknown parameter values, these beta and sigma square, that you will in fact never know. So if you simulate stuff, you know these things, but if you analyze data, you will never know them. This is why I always call them true but unknown, and they will always be unknown. And then you treat your data as one of these potential realizations and do all further inferences based on the distributions that we will today derive or look at least for the beta estimates and the sigma square estimates, and then later on, of course, for the t and f values. Yeah. Yeah.
So it's not a distribution of the true but unknown values, but of samples of the
yeah, very important and very good point. Yeah, so the true but unknown values, they are supposed to be fixed. So they are just fixed at numbers. So the distribution we are looking at is if we, based on these fixed true but unknown parameters, obtain multiple realizations, how do the estimates, how does the distribution of the estimates look like? This is also very different from Bayesian inference, because we are not talking about a prior distribution of our estimates or posterior distribution. That doesn't exist. That's not here. The distribution that we are looking at is what is also called the frequentist distribution of the parameter estimates, which, if they are then put together to form t or f values, actually give rise to the t and f distributions, as we will see next time. Yeah. Other questions? This is really, so ask if something is unclear, because this is really important for the whole thinking about the GLM. A lot of the GLM stuff is kind of mathematical techniques or so, but some things are fairly conceptual, and this is fairly conceptual, and yeah, we're getting to the real inference and evaluation then for the GLM in a frequentist setting. It's of course very different in a Bayesian setting, but we're doing frequentist statistics. Because everybody's worried about power. And then they are worried about positive predictive value, and they don't realize that they are making the shift to the Bayesian world there, but they don't care. They just say everything is underpowered. Anyway, good. So I hope this is clear. Of course, we will come back to that, and we actually follow it up now in more detail when we talk about the distributions themselves and also look at them. So that was kind of the intuitive part. And now let's have a look at the beta parameter distributions. Or distribution. Not that many. Yeah, so actually it is relatively straightforward to come up with the beta parameter distribution, and it actually just follows up from something that we actually have seen previously. So who knows? So we have looked at a similar thing previously. So we first talked about this distribution and said that epsilon is distributed according to this. And from this, we then came up with the distribution of py as this. Does anyone remember what we used to come up with that? So how we got from this side to this side? Apparently not. So what we actually used there was what I call the linear transformation theorem for Gaussians. And maybe you remember if I write it up in some form again. So what this linear transformation theorem says is if you have a random variable x, which is distributed according to a multivariate Gaussian with expectation parameter mu x and covariance matrix sigma x, and you now define a new random variable by multiplying x with a matrix A and adding some parameter b, so x would be n-dimensional and hence mu x and sigma x as well, and A would be m times n dimensional and b hence m-dimensional. Then we talked previously about how Z is distributed. Namely, we discussed that the fundamental result is, we also looked at an example in a one-dimensional case, that it's normally distributed. And does anyone remember what the expectation parameter of it was? Have a guess. Oh, what did I ask? I asked what is the expectation parameter of the random variable or random vector z that we already have stated that this is normally distributed or Gaussian distributed, but what is its expectation? Almost. No. Maybe 1/3. So the thing is, x, you have to think of x as a realization of a random variable. And you want now A plus B, yeah. Yeah, so A times exactly A times mu x plus B. So what you're doing here is to get a realization of z, you multiply a realization of x with a fixed number, and then you add something. Now, the nice thing about this multivariate Gaussian theorem is that you get the parameters of the distribution of z by applying the parameters of your transformation, so the A and B, to the parameters of the original distribution of x. Yeah. So you get a closed form representation of the distribution of z. Do you remember what the covariance matrix of z was, the covariance parameter? So the idea of this course is that you memorize everything. Because it's kind of, it's like learning and then coming out of a course and then knowing. That's kind of, anyway. So the covariance matrix was given by A times the covariance matrix of the original X times AT, which is fairly related to this notion that if you multiply a Gaussian random variable by a number, then the variance scales to the square of your multiple. But sorry, I don't want to go into the details again. We've done that some sessions ago when we talked about this thing here.
It is not mu times x, right? It is just mu x.
That's mu x, yeah. It's mu with a small x. Yeah, I could leave the x out actually. But I can also, for example, here write mu z is A times mu x plus mu b.
I thought it was mu times x and I was confused.
That's good. Then, Yeah, this is actually so for everyone maybe thinking about doing more theoretical work. These kind of things are so the properties of the Gaussian, they are really important, and they actually underlie the whole GLM theory, but then also any other analytical Bayesian inference theory or whatever for Gaussians, and Gaussians are important. Good. So this is what we've seen previously, and we used it at that point. We used it to actually we used it with the transformation matrix being the identity, and beta being actually B being x beta. That's how we used it back in the days. Today we're going to use it differently, but in the same spirit. So what we know is that our Py is, I draw a little box around this. This is just background. That our Py is x beta sigma square in. And now we actually defined a new and as we discussed, also a new random variable. So we discussed that it's random, and we defined it as xtx minus xty. So if you now basically try to apply this logic, you have, of course, have to exchange the nomenclature. This is a small x and is a random variable. Here it's a big X and it's a design matrix. But based on what is written above, one thing that you can definitely infer is that the distribution of beta hat is a normal distribution, because that's what the theorem tells you, because obviously you are just multiplying a normally distributed thing. But the question is, of course, what is the expectation of your of the estimate? So try to apply these formulas here. Try to apply them now to the expectation of beta hat. And don't try to simplify things. Just try to tell me what the formula says, what it should be. So what is A? Now? Have a guess. What is A? It's not kangaroo, and it's neither crocodile. So what is A? Come on!
X transpose X to the 4 minus 1 times X transpose.
Exactly. And if I now use that A, with what do I have to multiply to get the expectation parameter?
X beta.
Mm-hmm. So what I get is xtx minus 1 xt times x beta. Yeah. So that's the expectation parameter of the distribution of the beta estimate.
Do they cancel out?
And as you rightfully say, these two cancel out, because this is the inverse of this, so you get the identity. Hence we obtain that the expectation parameter for the beta hat estimator is beta. What is this beta? Well, this is the true but unknown value, right? So think again in terms of the virtual simulation. You can only simulate this here if you fix some true but unknown value for beta and sigma square. And what this now says is that the distribution of the estimate has as expectation the true but unknown value. which is good because that also means that it's in terms of the mathematical statistics nomenclature unbiased. So on average, if you think again in terms of sampling over many repeats and treating expectations as long-range averages, on average, you actually estimate your true but unknown beta parameter very well. The next thing is the covariance matrix of the beta estimate. What do I get there? If you again think of what A is.
That thing in front of y times sigma squared, I don't think it's that, and then again the transpose of the phrase in front.
Yeah. And this can also be simplified to a certain degree. So the first thing that you see here is that there is a scalar somewhere in the middle. If you have that in a matrix product, you can always get the scalar out first. Then you have the identity matrix, which doesn't do anything, so you can get rid of it. And then you have the transpose of a matrix product, and you might recall that there is this rule for multiplying matrices and transposing them that looks like this. That helps to a certain degree, so it tells you that this the last thing, this xt transpose, should come first and be transposed, and the transpose of a transpose is what? X, exactly. And the thing that doesn't really, that you should be unsure about is actually what happens to the transpose of this. But because, well, we can just write it down first. So we have here this. Oh, it looks horrible. And it turns out that actually this is a symmetric matrix which one can show based on this xt times x, and then the inverse is also symmetric, and then the transpose of this is again the inverse. But this is something that you should have severe doubts about if somebody tells you and you don't see a proof. But I'm telling you now, and hope that you trust me. Otherwise we cannot go on. And I speculate that you will trust me because you want to go on. You want to go on Christmas holiday. And then we get this, which we can then also look at in a little bit of a simplified manner. So can get rid of the brackets. Maybe let's get rid of the brackets. And then we see that again we have here one thing that cancels out. So what we end up with is only this first bit. Yeah. So we can actually maybe let's write it up nicely again. So we get n beta hat beta sigma square xt x minus 1. So this is the distribution we get for the beta parameter estimates. And this already, if one just looks at it, has definitely two implications. So first of all, long range or large sample, not a long range, large sample average. So if you think about getting many realizations, so data realizations, and hence many parameter realizations, and then averaging over these parameter realizations, the long-range average of these will be beta, which is true. So which is the true value, true but unknown value. That's good, which is not always the case. The other thing that plays a role is that it's definitely the variance parameter. So if error variance, because remember this sigma square is just the if error variance sigma square is high, then also the variance of beta hat is high. And then finally, and we will, let's see how much we will look at that. Finally, design matrix influences the beta hat variance. Yeah, so this is what one can see from basically just what we did. So this, there are multiple implications. So this means that this is actually a good thing. So on average, if you get realizations from the GLM, or if you think in more data analysis terms, if you do the same experiment under identical circumstances again and again, and you average together your estimates that you obtain each time. So if you essentially doing reproductions of your experiments, and then over many years average what you got, then you get closer to true but unknown values. However, how often you need to actually do this depends on the true but unknown error. So if that is high, then you will have to sample a lot, and then sometimes you will find that you have, for example, a positive beta effect, and then somebody else will not be able to reproduce it. And then it's like, oh, it's not reproducible, but then maybe let's reproduce it again, and then you will find it again, so you can go on reproducing your experiment. And finally, you have in terms of designing your experiment, you have a way to deal or to influence the variance in your estimates by changing your design. So by this, you have a way to actually do something such that the variance of your estimates is not that large. This is a topic in its own, which for fMRI data we will likely encounter in the summertime. Yeah, questions about this right now? No? Good, so then let's look at a visualization of this. So this is again is a visualization for simple linear regression. So assume that you have this, and based on true but unknown parameter values, you have what we've seen now multiple times. You have kind of this expectation this expectation vector. Yeah, so that's your x beta for true but unknown values of beta, which, for example, are, so that if this is 1, so then we have an offset of 1, and let's say also a slope of 1, just to make it easy. So your true but unknown beta parameters are 1 and 1. Now you can obtain a sample. So let's obtain one sample. And just to make clear that this is one sample, I'm connecting the dots here. And we can look actually at the realization of the beta estimates. Let's make this blue maybe. So let this be, doesn't really matter, beta 2, and this be beta hat 1. Then first of all, we can of course also in this graph plot our true but unknown values. So let's say this is 1, this is 1. So the true but unknown values are of course here. Yeah, this is now not a data point or something. This is a point in parameter space. And then we can get a realization here. I don't know, it's a little hard to guess. So the slope, maybe the offset is a little bit off. So maybe the offset is a little bit larger. So this would be the point that corresponds to the to this sample. Yeah. So this is a sample which now is mapped onto this point in parameter space. And then, of course, like I said, we can get another sample. So let's make a sample that is always really off. So this sample then gets mapped maybe to a point here. So let's don't pin me down on the numbers right now, just try to get the idea. Then we have another sample, maybe this looks like this. Of course it gets a little bit messy. And then we get point here. You see on figure 10, you see these samples that I'm just drawing, you see them without lines connecting them. So you don't really know which points correspond to one sample, but you at least see a number of points. And then the crucial thing is that if one looks at the distribution here of these beta parameters, if one gets more and more samples, they start to look somewhat Gaussian-like. And what we have derived here, so our formula that we have up here, so our n beta hat beta sigma square xt x to the power of -1. This is actually, again, of course, a analytical description of Gaussian, which we can describe in terms of its probability density with something like this. Well, that's a good question. It is tilted. Even if I could only draw something tilted, something like that. It is tilted and not spherical because here you don't have the identity matrix. So it's very likely that if you look at this, for example, you transpose it and then so you multiply it with itself, so it becomes a 2x2 matrix, and then you invert it, that this is not the identity. However, this is as much as I can say. So why it takes actually this tilt in this direction, I mean, it definitely that depends on how, so in which order you put in these numbers, and that it is, so that is not the identity. Is relatively easy to see how it is exactly tilted. I can't, also how to infer from how the design matrix looks to how tilted the distribution is. I think that's harder to infer, or at least I can't do it. But one thing that is of course important, the whole spread here, so how much the parameter estimates spread in parameter space, that is of course also determined by this scalar parameter. Yeah. Good. So that is the figure 10. Yeah. So again, this is beta hat 1, beta hat 2. And this is kind of the sampling way to look at it. And this is the analytical way to look at it, if you want. Okay, questions?
There is no way to calculate that, right? The true but unknown.
No, the true but unknown values, they will always be unknown. And once you realize that, you don't get so anxious about science. You relax and say, well, the true but unknown things will always be unknown, so I can do my best to, for example, make a design that minimizes the variance and so on. But here in my experiments, I have one result, and who knows what the true but unknown values are. So, and please don't believe any results ever, because you know that the true but unknown values will always be unknown. Good. Then let's have a break and look at the variance parameter after the break.